In this video, we're going to be talking about multiple regression. Now, last chapter, we looked at simple linear regression. And with that model, we were only able to have one independent variable. We had one variable that we could use to explain our dependent variable. However, in a lot of cases, it's not that it's not enough, but that we might want more than one independent variable. There may be more than one variable, one thing that explains changes in our dependent variable, our y variable. That's where multiple regression comes in. Multiple regression is just an extension of simple linear regression in that we can have more than one dependent variable. So let's look at the model. So a lot of this stuff is going to be similar to what we looked at in chapter 13, but there are going to be some significant changes. All right, so again, let's start with the model. So hopefully this doesn't look too different for us. When we're looking at this, just like in our simple linear regression, we have multiple variables, right? Just more of them this time. So yi, that's going to be the ith observation of our dependent variable, whatever it is that we're trying to predict, what we're trying to get a predicted value for. Beta naught is going to play the same role. This is a constant. It is the slope intercept. And again, since we're looking at, not again, because I haven't said it in this video, but since we're looking at the model, this is the slope intercept for the population data, right? So this is the model, so these are the population parameters. All right, and then we have our x's. So now we just have more of these. These are still our independent variables. We're going to have more than one, so we're going to have more than one x. We can see that our x's, in a simple linear regression, it was just xi. Now it's x1i, x2i. So this is just, so for x1i, this is the ith observation of the first independent variable. x2i, it's the ith observation of the second independent variable. xki, it's the ith observation of the kth independent variable. And k is going to be important. So k is the number of independent variables we are looking at. So however many variables we are using to predict our dependent variable, that is what k is. And then our betas, beta 1, 2 through beta k, these are our slope coefficients. I just realized, I think I called this the slope intercept. That's not what it is. It's the y-intercept, right? It's where the line would intersect the y-axis. So just want to make that clear. This is the y-intercept for population data. These are the slope coefficients, right? These determine the slope in conjunction with the values of those independent variables, right? Also, just in a broader term, beta 1 is the effect on the dependent variable that x1 would give, right? Beta 2 is the effect on y that x2 would give, so on and so forth. And then, of course, since this is the model, we are including our error, this epsilon here. Because no model is going to be perfect unless all of our data is perfectly linear, which that is very unlikely. And of course, since the model is for our population data, and population data is kind of hard to come by in a lot of cases, we're not going to be able to actually get those betas, right? We're not going to be able to get beta 0, get beta naught, beta 1, beta 2, so on and so forth. So we're going to estimate those betas. We're going to use sample data to estimate those, and that's going to give us kind of the sample is going to give us the estimated regression equation. So our estimated equation is going to look like this. Again, this hopefully does not look too unfamiliar, right? yi hat, again, when we get to our estimated equation, we are no longer getting the actual observed value for y, for our dependent variable. We're now looking at a predicted value. So yi hat is that predicted value for y. B naught, that is our y-intercept for the sample data, and so on and so forth. The x's don't change. And B1 is the estimate for beta 1, B2 estimate for beta 2, so on and so forth, right? And again, not again, because we haven't covered it, but just like with simple linear regression, once we get to the estimated equation, we drop that error term off as well. So let's actually put some of this into practice. Let's say that we want to estimate wages, right? We want to estimate an individual's wages. Now, there are several things that could go into an estimation of wages, right? There are a lot of different factors. Some factors like how many years of education do you have, right? Because the higher your education, we know the higher your wages are on average. Also, how many years of experience, we might want to include that. The more experience you have in a certain field, the higher your wages are likely to be. We'll keep it right there for now, but there are other factors. We're going to get to some of them. Some of them we're not going to get to. But let's say that we want to predict hourly wages using the number of years of education a person has and the years of experience. So how much experience do you have? Now, with simple linear regression, we would have to pick one of these to put into our model, but we don't have to do that with multiple regression. So let's go ahead and write out our model for this regression. And I'll be kind of condensing some of these things into variable names. So actually, let's just erase this. So again, right before I erase it, we're going to predict hourly wages. That's what we want to predict, using the number of years of education or years of education and years of experience. All right, so since we're wanting to predict hourly wage, that's going to be our dependent variable, that's going to be our y. And we're just going to call that variable wage. So wage I equals beta naught plus beta 1, and then doesn't really matter which order we put these in, but I'll just use the order that I did on my notes. So we're going to put years of education first. I'm going to condense this to EDUC, EDUC. So education to save some space, plus, actually we might want to just come down here, plus beta 2 times years of experience, expert EXPERI, and then of course we don't want to forget to include the error term. So this is our model, right? We are not going to actually estimate this by hand. I made you estimate some things by hand with the simple linear regression. The reason for that is because it's relatively simple. Once you start adding multiple variables, we're not going to be able to do this calculation easily, unless you're getting into kind of linear algebra, which I don't think anybody wants in this class right now. We're not going to be able to do that. So we're not going to worry about that. Luckily, there are a lot of statistical programs like Minitab that are going to do this for you. I intend to put up a video, hopefully shortly after this one goes up, that kind of walks through some of these things, not only showing you how to perform a regression or multiple regression analysis in Minitab, but also how to read the output from that analysis. All right, but like I said, we're not going to do that. I already have done that. So we are using some data from a 2008 CPS, which is a current population survey. So this is kind of like a mini census in between censuses. Censi? I don't know what the plural census is, but anyway, regardless. So this is actual data. The sample size is 1,000. I'll write that down again when it becomes relevant. So this is actual data from actual people. So I did my estimated equation. So again, now that it's the estimated equation, we need wage I hat. Wage I hat equals negative 11.750 plus 2.068 EDU CI or EDUC plus 0.145 experience I. All right, so that is our estimated equation. So again, just I'm going to erase this in a second and move it up so we can talk about it a little bit more. But again, just some differences between our model and our estimated equation. Remember that the model is for the population, so it's going to be in parameters. We're never actually going to do anything with the model other than just setting it up, really. And when I want you to do this, this is just so you show me that you know what your dependent variable is, what your independent variables are, so on and so forth, right? So big differences here in the model. This is the actual observed value for our dependent variable. In the estimated equation, we have the predicted, right? So there is a big difference. In the model, we have our error term. In the estimated regression equation, we don't have an error term, right? And then finally, in the model, we just have betas. In the estimated regression equation, we actually have estimated values for those betas, right? B0, B1, right? We have actual numbers and not just symbols. So actually, I'm going to write that equation down again in just a second. Before we do that, let's talk about interpretation. That's why we're going to write that down later anyway, so we can actually interpret some of these. So to talk about how to evaluate B naught. I believe I said this in the video for simple linear regression, or one of the videos for simple linear regression. Beta and naught, a lot of times, we're not too concerned about. We really weren't that concerned about it when we were talking about simple linear regression, all right? Even though it was one of only two things that we were estimating. But we really don't pay it much mind when we get to multiple regression. The reason is it's really just a placeholder, all right? With all the other variables working, those are what we're interested in. Those are the effects we're interested in. And a lot of times the constant just doesn't make that much sense. But similar to how it was interpreted in simple linear regression, where it's the average value of our dependent variable when the independent variable equals 0. B naught in multiple regression, it's the average value of the dependent variable when all of the independent variables equal 0. So average value of y when all x's equal 0. Right, again, average value of the dependent variable when all independent variables equal 0. So for B1 through BK, these again are going to be very similar. The interpretation's very similar to how we interpret them for simple linear regression. It's the unit change in y for a 1 unit change in whichever one we're looking at, right? Actually, let's see. I'm going to just write this as BI, and 0 is not included in this, all right? So let's say for the i's, they have to be integers, so 1 through whatever, 1 through k in this case, all right? So So the interpretation for BI is that it is the change in our dependent variable for a 1 unit change in the particular independent variable, right? So this probably make more sense when we actually do some examples. But again, right, a 1 unit change in xi is expected to lead to a BI unit change in y, or the dependent variable. All right, so for our model here, all right, so if we were to interpret these, I'm not going to write these down. You can go back and rewatch it if you need to hear them repeated. Also, I'm probably going to say them like 5 times anyways. So let's first start and look at our constant, negative 11.750. So in this context, right, we're saying the interpretation of B naught, or our constant, is the average value of our dependent variable when our independent variables are 0. All right, so 0 for education would mean 0 years of education. For experience, it would be 0 years of experience. So our interpretation could be something along these lines. I would expect an individual with 0 years of education and 0 years of experience to have a wage of negative $11.75, right? So $11.75. You can kind of see why this isn't very reasonable. Because even if you have no education and no experience, there are still jobs that you could get that you would not have to pay somebody to have, right? That doesn't make a whole lot of sense, and that's okay. The intercept is usually pretty squirrely when we get into just regression in general, and especially when we get into multiple regression. Again, it's also just not the thing that we care that much about. We're much more interested in the effect of a year of education or a year of experience. Right. So when we're interpreting these, the word or words of the day are all else equal, right? If you've had an economics class, you might have heard it as ceteris paribus. It's the same thing, it's just Latin for all else equal. We're holding everything constant but the thing that we're interpreting, right? So for instance, if we're interpreting the effect of one more year of education, right? So in other words, interpreting B1, then we could say something along the lines of, I would expect an additional year of education to increase wages by $2.07, right? So rounding that up a little bit. All right, that is under the assumption that experience doesn't change. So all else equal, right? If nothing changes but an individual gets an additional year of education, right, I would expect their wages to increase by $2.07. All right, again, a couple of things we need to look out for when we're interpreting these, right? What the sign is of our coefficient. If it's positive, that's going to show us an increase. If it's negative, that's a decrease. Right? We also want to make sure that we keep things in the units, right? A 1 unit change in X leads to a B1 unit change in Y. Right? We want to make sure this is education is in years, so those are the units. 1 year increase, $2.07 increase in wage, because wage is in dollars. All right, but just again, and then I'll do the next one. All right, I would expect, and again, also, I keep saying again, I haven't told you guys this yet. The reason I'm saying I expect is because it's not guaranteed. Getting another year of education doesn't guarantee that your wages go up by $2.07. Right? This is kind of an average. This is what we would guess, what we would predict. Right? I would expect an additional year of education, or a 1 year increase in education, to lead to a $2.07 increase in wages. Right? Then let's go on to, I think we got that one, hopefully. Let's go on to the next one. So experience. So here I would expect a 1 year increase in experience to lead to a 14, or you could round that up to 15 cent increase in wages, right? So we'll stick with